I would like to express my appreciation for inviting me to give a talk at this very important event. Today, I'll be talking about the development of the brain. And there are some anatomical facts in connection with this talk. There is no single brain region that operates in isolation, and the brain is indeed a complex network of neural interactions. It contains about 100 billion neurons and lots of lots more synapses. Synapses are connections between neurons. On the average, a single neuron has about 7,000 connections, and the peak age for connections for synapses is at the age of 3. This is a picture that shows the development of the brain in embryonic life at the earliest period of embryonic life on the top left, while the bottom right is what the brain looks like shortly after birth. There are two phases of brain development. We have the prenatal brain development and the postnatal brain development. The prenatal is occurs before we are born, and neurulation is the foundation for which central nervous system development builds on. And once neurulation is complete, we do proceed to generation, proliferation, and migration of the neurons. The neurons are the basic cells of the nervous system. The neurons then get organized, and myelination, which can also be thought of as a process of insulation, begins. Um, Postnatally, formation of neurons is less prominent, but still does occur. What is more important in postnatal development is connectivity, which is the formation of synaptic connections among relatively distinct structural areas of the brain. Postnatal connectivity is an exuberant process. Connections in the developing brain greatly exceed those found in the adult. Interestingly, input through the senses is a driving force in brain development. The cerebellum also continues to develop postnatally, and neurogenesis and migration continue into adulthood in the hippocampus, which is a very, very important part of the brain. And neurogenesis has also been observed in the olfactory bulb. There is a remarkable increase in brain volume during the first 2 years of life, and this is predominantly accounted for by increases in the gray matter volume. The cerebral cortex has a greater volume relative to brain size in children than that of adults. In early adolescence, a peak of cortical volume occurs and then it starts to decrease. Neuroplasticity is the dynamic ability of the brain to organize itself after injury, during learning, or during our daily life-to-life experiences. Physical and psychological inputs can have an input into the pattern of connectivity that develops in the brain. Neurogenesis can also contribute with the neurons coming from the neural stem cells. This potential is one of the scientific bases for rehabilitation, that is physical rehabilitation, then transmagnetic brain stimulation, brain-computer interface therapies, which improve neurological and neuropsychological outcomes in brain-injured patients. The concept of neuroplasticity allows short, middle, and long-term remodeling of neurosynaptic maps to optimize functioning of brain network, and it plays a critical role after injury or damage to the nervous system. As an illustrative context, removing one cerebral cortex in a small child does not lead to inability of the child to walk. Neuroplasticity does play a role in the rehabilitation of brain injured patients. In conclusion, brain development does not end at birth. Neuroplasticity allows functional brain recovery from injury and some other diseases over time, be it in the short or long term. Sensory and psychological input does influence brain development and recovery, and this emphasizes the vital importance rehabilitation plays in optimizing recovery from neurological injuries, and also emphasizes the importance of such initiatives that is being taken today. Thank you very much.